Hi, and welcome to the third video in this series about implementing big integers in C++. In the previous episode, I wrote the addition operator and discussed potential optimizations, which were not so impressive because the compiler is very good at optimizing. One big takeaway is that micro-optimizations look ridiculous altogether in the light of how much time is lost when there's a memory allocation going on. Per my testing, runtime increased tenfold when using operator plus instead of plus equals. I think it is worth digging into this to understand what exactly is going on. Spoiler, this is more related to my test loop than the benefits of plus equals over plus. I used a slightly different test loop, which does 1 million iterations in total, adding two 3-word numbers, which overflow when added together. I ran 3 versions and profiled them with instruments. With operator plus adding a plus b, we have roughly 2 million allocations. 1 million of 32-byte blocks and another 1 million of 48-byte blocks. This was kind of expected because in the inner loop, allocation first occurs in the copy constructor here, and then a second time, if there is an overflow, a second allocation happens in the addition code. Let me scroll. Yes, here. That's the second allocation. And it looks like the return has been optimized out. So we only have 2, not 3 per cycle. And that's how we get to 2 million allocations. Why are the blocks 32 and 48 bytes? Intuitively, the smaller one corresponds to the copy constructor and the larger one to the overflow. But wait, my numbers are initially 3 words long and grow by 1 word. So why didn't the allocator request 24 and 32 bytes respectively? There could be several reasons for that. Number 1 is that the compiler will typically round up the block size to a multiple of 16. This depends on the implementation and on the architecture. So 3 times 8 is rounded to 32, but that doesn't explain 48, because 4 times 8 would fit into 32. Now comes the second reason. std vector does its own memory allocation optimization. On resize, it may increase capacity beyond the new size in order to avoid frequent reallocations. So when a vector is resized from, let's say, size 3 to 4, new capacity can be increased to 5 or 6, but this is not guaranteed. So this would explain the 48 bytes. Final thought, the allocated block is always larger than the requested size to store allocators overhead, which should be 8 or 16 bytes. I'm not sure whether instruments reports gross or net size. So let me know in your comments. Back to the 2 million allocations. If I change my test code here, so instead of a plus b, which was stupid, I do c plus b, which really replicates plus equals. Now, in instruments, you see that the 1 million of 48-byte blocks is gone. It's down to 100 something. And the reason is that once C has grown, there is no further overflow in the inner loop, and therefore no calls to malloc. More precisely, the first iteration in the inner loop allocates 3 words in the copy constructor to create C, and then allocates 6 words on overflow. But all subsequent iterations in the inner loop allocate exactly 4 words because the copy constructor discards the capacity beyond size. And there are no more overflows, so that's how we get 1 million of smaller blocks and about 100 of bigger blocks. Now, let's look at the third version, C plus equals B, which is the most efficient. And here we reduce drastically the number of allocations. We were talking hundreds, not millions anymore. In the outer loop, we call the copy constructor to create C. We had this in the previous run, but it was immaterial. So that's 100 of 32-byte allocations. In the inner loop, plus equals avoids calling the copy constructor, but there is still a 48-byte allocation when there is an overflow. And this happens only once per outer loop iteration. So that makes a total of 100 allocations of 48 bytes. The bottom line is, operator plus is inherently inefficient because its semantics imply creating a new object. But if it was okay to abandon operator plus and write a function, it could look something like this. Let's call it add in place, const longer reference A, const longer reference B, longer reference result. And well, inside it would be something else. But the idea is to write the result directly in a pre-allocated object, which means that allocation would be handled by the caller, which basically moves the problem elsewhere, but chances are they can do it smarter. Otherwise, if it must remain operator plus, I think I could at best mitigate the second malloc call by reserving max plus 1. And so we would have const longer reference A, const reference B, and we would create still a temporary object. We would reserve a bigger size at plus 1, and we would temp plus equals B, return temp. This actually addresses a different problem, which is not related to operator plus semantics, but is an intrinsic problem of optimal resizing that we already have in our addition code here. It's the dilemma of either to resize to max size plus 1 in the beginning here, or conditionally extend the size in the end if there is a carry. So the question is, can we predict the carry and know in advance whether we need the plus 1? The short answer is no. We can't predict it with certainty. Or rather, predicting it with 100% certainty involves actually performing the addition, so it's no good. There are some techniques that produce false positives, and typically they look at the most significant limb or the most significant byte, so there is a way to optimize a little. But I believe that it would not be a game-changing optimization, so I will not implement it here right now. And given that we can't predict the carry, which path is better? And the answer depends on the numeric input. Consider the first scenario, where the second operand has at most the same length as the first. In this scenario, the first resize here to max size does nothing. On the other hand, if we were to resize to max plus 1 here, it would systematically extend the vector, which is not needed in most cases. The probability of overflow depends on the data. It should be very low when numbers represent some real-world value, but if you are dealing with random numbers where each byte is populated, I believe the probability should be around 50%. So the option that I have here to resize lazily in the end is always either better or equal than the other one. But now consider the alternative scenario, where the second operand is longer than the first. The first resize will always extend the vector, whether resizing to max or max plus 1. And the probability of overflow is the same as in the previous scenario. So here the best option is to resize to max plus 1 in the beginning, avoiding a potential second extension. So now I think I'm ready to implement a small optimization. If the size of this is less than the size of the other, then reserve max size plus 1 and resize to max size. And we still keep the conditional resize in the end. Another idea is to always over-reserve, so that resizing to max plus 1 does not actually call the allocator. This could boost performance in some use cases, but there are a few things to consider, some of which I have mentioned already. So I would need to write custom allocation logic in copy constructors and assignment operators to reserve n+1 items. Is it okay to do that? In C++, a copy constructor traditionally promises that the new object will have the same value as the original. That means same elements, same logical state, and same observable behavior. It does not promise the same capacity, memory layout, or allocation strategy. So probably we should not copy this hidden non-semantic state, which depends on the past growth history, allocator behavior, and reservation strategy. Besides, it would be an additional layer of size management over std vector's existing logic, which is happening under the hood. Last but not least, it would make everything bigger and longer to process. Overall, I see some pros and many cons, and would rather not implement this for now. One more thing. I made a case against micro-optimizations. To prove it again, I tested whether this condition was evaluated on each loop iteration. The answer is no. The compiler already hoisted it, so it's evaluated only once before the loop. I also tried a few things here because I heard that in place back was the most efficient way to add a limb to a vector. It did not help, it was actually slower. I also tried this, and it wasn't faster either. Why so? The short answer is compiler optimization. I think that's it for today. Thank you very much for watching, and see you next time.